right, so our plan is just, I'm going to take your questions like usual during office hours. Quiz 5 is due today, and then we're getting ready next week to turn in the problem set and take the test. I'll have Chapter 5 material posted by Monday, maybe a little sooner. But our focus this week is just making sure that we get Chapter 4, put away. So any questions on this work that we're doing?
I have a question regarding the earn points back for that last.
Oh, sure.
So where do you want us to turn that in? Would you?
I think you can. I think you can turn it in, like in that link for test 3.
Okay, that's
like
right.
I think it'll make you have a new. I think it'll make you make a new. Sorry, I think it will let you make a new submission, and you could just upload that. If that doesn't work, you could do it, attach it to a comment or something. But I'm pretty sure it'll let you make a new submission.
Okay. Thank you.
Mm-hmm.
Could you go over number 3 on quiz?
Yeah. Let's see. Let me just take a look. Yeah, okay, so with this one, sorry, hold on. Okay. So we have this spotlight or a searchlight 220 feet from a straight wall. They've given us a figure, which is helpful. This is the beam. Here's the wall. This is the angle theta. We know it's 225 feet from the wall, so that side is fixed. And they tell us that the angle between the beam and the perpendicular to the wall, that's theta, is increasing at 1.5 degrees per second. Oops. And then we want to know how fast is the length of the beam increasing. So the length of the beam, I'll just call that x. What kind of problem is this?
A related lengths.
Right, yeah, because they're telling us the rate at which theta changes, and then they want us to find the rate at which x is changing when x is 315 feet long. Okay. A rate is a derivative, right? That's one of our big takeaways from the whole course, is that a rate of change is a derivative. A derivative is a rate of change. So when they tell us that theta is increasing at 1.5 degrees per second, what in sort of calculus terminology, what have they told us?
D theta over dt equals 1.5?
Yeah, sort of. You're like super close. That's definitely d theta dt. When we're relating trigonometric functions to like lengths and distances, remember that we have to have our calculators, our hearts, and our minds in radian mode. So you actually want to convert this to radians per second.
It'd be pi over 120, right?
Yeah, great. Right, you just find that by multiplying by pi over 180. Awesome. So that's our no, right? That's what we know. And so what we want, what's the derivative that we want?
dx over dt and x will equal 315.
Yeah, we want dx dt when x is 315. So, you know, you've got, it's all organized now. We've identified the rate that we know, we've identified the rate we want to find. The only thing that's left is to, I guess, have an equation that we can differentiate. So looking at this diagram, I know it doesn't look it, but that's a right angle there. What's an equation? We need our equation, you know, the rate that we know is theta, the rate that we want is for x, so we need our equation to involve that angle and that side. And then it's silly to involve another side that isn't fixed, you know, so if I can use a length that's fixed, I'm going to. If somebody really wanted to, they could use Pythagoras and get an expression for this side and then use that side instead, but that would just be a lot more work. So what's the equation that you're going to start with?
Cosine theta equals 225 over x.
Right, adjacent over hypotenuse. And then what do you do with that? What can we do from here, Daphne?
You can split the 120, so you can do 1 over x times 125.
Yeah, or 225, but yeah.
Oh, yeah.
1 over x times 225, or I might even go just one step further and call it 225 times x to the minus 1. Just because I think that'll make the derivative easier. Now, I'll point out right now, there's two approaches, right? There's one where you could just use the trig function, the cosine function, or if you like, you could turn that equation around. If cosine theta is 225 over x, that means theta is arc cosine of 225 over x. And they're both fine, you know, you'll get the same correct answer either way. So it's kind of up to you which way you want to go. But the idea is once you have an equation that relates them together, right, what's your next move?
Take the derivative.
Yeah, exactly. You'll take the derivative with respect to time on each side. What do you get on the left side when you do that?
Negative sine d theta over dt.
Yeah, negative sine of theta, and then times d theta dt. The d theta dt comes about as a result of the chain rule. And what about the other side?
X times 0 minus 225 times dx over dt over x squared.
Say that again.
It would be x times 0 minus 225 times dx over dt all over x squared, right?
Oh, you're using the quotient rule on this. So x times 0 minus 225 times dx dt all over x squared. Yeah, and you could do, yes. So that's what you get if you use the quotient rule on that. The reason I thought maybe we could rewrite it this way is because when you take that derivative, it's just a power rule. But that's what you get when you are finished, right? Because the x times 0 goes away, and you have minus 225 over x squared times dx dt. Yeah, so, I mean, at this point, I think you're well on your way. You know what d theta dt is. You could solve this for dx dt and then evaluate it when x is 315. What you'll have to do is figure out what sine theta is when x is 315. But when I think that one of the easiest ways to do that is to go up here to this figure and say, okay, well, when x is 315, then my triangle looks like this. And you could solve, for this side, maybe I'll call it y or something, and use SOHCAHTOA to get sine. Or when x is 315, you can use arc cosine to figure out what theta is, and then plug that into the sine function and get the value for sine that way. Other questions?
Yeah, I had a question on number 1.
On the quiz?
Yeah.
Okay, so the first one says they give us a function. They say f of theta is equal to 1/4 times sine squared of 2 theta. And we want to find f prime of theta, so we're just finding the derivative. So how did you start this problem?
I started it with d theta over dt equals 1/4 parentheses sin parentheses sine and parentheses 2 theta close parentheses squared.
So 1/4 parentheses sine parentheses 2 theta, and then what?
And then close the parentheses one more time and then 2.
Okay, yeah, so that's not quite what we want. So you also said d theta dt. If we were differentiating with respect to time, we'd have a df dt probably, and we'd have a d theta dt involved. But we're just finding the derivative, so we could call that f prime of theta. Or if this function we called y, we could say, oh, we're finding dy d theta. But when they asked us to find the derivative, f prime of theta, we are respecting theta. So it is with respect to theta, the one variable that we have here. So let's, the first thing I'll do is just encourage you to rewrite this function. When I take this derivative, before I take this derivative, I rewrite it and I say, okay, my function f of theta is 1/4 times. Now sine squared 2 theta, that's what I get if I take sine of 2 theta as a function, the whole thing, and square it. And when I write it that way, it makes it easier for me to see that this is a squaring function. I'm raising stuff to a power.
Yep, that's the way I wrote it.
Great. So then when you find the derivative, you're going to start with the power rule. Which you will have a factor of 2 that you'll bring down with the 1/4, right? And
Yeah.
you will have a sine 2 theta to the first. But you're just not done, right? So when you find f prime of theta, you have this that you started out with. But part of the power rule is that we have n times u to the n minus 1 times du dx. So this part you got, right? You did that part, but you've left off the chain rule. So we have to multiply by the derivative of the stuff inside. You have to multiply by the derivative of sine 2 theta.
Which would be cosine 2?
Cosine, well, the derivative, so our rule is the derivative of sine u is cosine u times du dx. So the stuff inside stays the same. So what is this derivative going to be?
Two, it would be two,
Theta, yep.
theta, two theta.
And then, what about the chain rule that's a part of taking the derivative of sine of u?
2 times 2.
Yeah, and that's it, right? That's the derivative of 2 theta is just 2. And then you're going to clean it up. If you are finding, like, if, the chain rule, I guess we call it a chain rule for a reason. Sometimes there are several links in it. And if you find that sometimes you're making mistakes or leaving off parts of the chain rule or forgetting to implement it, I will encourage you to spend some time on the exercises for these first couple sections. So there's the derivatives of the trig functions in sections 2.4 and 2.5 here, and then derivatives of the inverse trig functions, and that'll just get you some practice on implementing the chain rule there. Other questions?
On the problem, I had a question on problem set number 4.
Mm-hmm. Hold on. Which one?
Number 4.
Okay, so in the top it says you might find it helpful to refer to example 423 in the notes. So oh, here it is. So in example 423, we have a similar problem where our function involves, it's like exponential, but not quite, because we have a variable in both the base and the exponent. So what we did was we used logarithmic differentiation. We started by taking the log of both sides. And once we did that and used the property of logs that said we could bring down that power in front as a factor, then we were able to differentiate both sides. We just had to use the product rule on the right side. So I think you'll want to use this one as a model for how you approach that problem. Is that something you had already tried?
Yeah, I already. I tried to figuring it out, and I was just having trouble with it in general.
Okay, so so what did you do first?
What I did first was dy over dt equals x
So what does that example 423 suggest that we should do first?
It suggests is that we should bring down the x into the front.
That's not what we do first.
Multiply both sides by ln.
Yeah, and it's not actually multiplying. We're just taking the ln of both sides. We're applying the function. As ln's a function, not a factor. But yeah, so look, the first thing that we did here, Tyler, was this is what we started with, right? And this is what we did first. We took the ln of both sides. So that's how you want to start this one. And, you know, the only reason we would take the ln of both sides is because there's some property of logs that we're going to find helpful, right? Otherwise, it seems like we're just making something complicated. But the log should help us. So what property of logs could we use here? And in fact, I think I'll take a look at these notes. There's, we started in this section just reviewing the properties of logs. We said we could split up logs over a product inside. We could split up logs over a quotient inside. We could, if I'm raising the stuff to a power inside a log, we could bring that power down in front. And if you look at what we did in example 423, the next thing we did after we took the ln of both sides is we said, look, here's this, we were raising stuff to the sine x power, and then I'm going to bring that down in front as a factor. That's using that third property of logs. So that's what you want to do next. And that's as far as I'll get you this time around on this problem. From here, you can take the derivative of both sides. And by the way, you're respecting x, not t, right? We're just going to find dy dx in this problem. But you're going to differentiate both sides with respect to x. And you can use the product rule on the right side. And then I'll just, I'll encourage you to have that example 423 kind of right in front of you as you're working through this problem. And then if you get stuck, or if you think maybe you have it but you're not sure, you want me to take a look at like a draft of your solution, like I'm happy to do that. You can send me a message over Canvas or something. But this should get you started on that problem. Are there other problems you want to ask about?
I guess problem number 5.
Mm-hmm. So with problem 5, we want to, so they give us an implicit function here, and then we want to show that dy dx is equal to negative e to the y minus x. So it's kind of like saying find dy dx, but they're telling us what we should get. So this one can be a little tricky for one reason in particular. So we have e to the x plus e to the y equals e to the x plus y. Now that's not generally true, right? I mean, that's not like a property of exponents at all, but we're defining a function or a relation between x and y. The universe in which this problem exists is the one in which these two things are equal. and we're going to show that dy dx is negative e to the y minus x. So, I mean, I would start this the way you would do any implicit problem, which is just differentiate both sides with respect to x. So, if I differentiate with respect to x on both sides here, what do we start? How do we start on the left side?
You would have x e times dx, times d over dx.
Well, it would just be so the derivative, we're respecting x here, right? We're not respecting t or anything, so we're using the derivative formula we need here is that the derivative with respect to x of e to the u is e to the u du dx, right? So e to the stuff is its own derivative, except that we just have to follow up with the chain rule by multiplying by the derivative of whatever is in the power. So if I take the derivative of e to the x, I'm going to start with e to the x. And then the derivative of x is 1. So you could multiply by 1, or you could leave that factor of 1 off, if you like. What about e to the y?
Wouldn't it also be e to the y times 1?
Well, it'd be e to the y times, now we have to remember that we're respecting x and this is a y, so what do we need to multiply by?
D over dx?
dy over dx. What do we get on the other side?
Would you get e to x plus 1 times dy over dx?
So e to the x plus y times, now we have to multiply by the derivative of x plus y. There are two terms in that exponent. If I take the derivative of x plus y, there's going to be two terms in that derivative. The derivative of x is what?
1.
And 1 plus, what's the derivative of y?
dy dx.
Okay, there you go. So there, we just did the first step together. All right, what you're going to do now is use algebra to solve for dy dx. I'm going to tell you ahead of time that when you do that, you're not going to get this at first, right? You know, remember, our goal is to get this negative e to the y minus x. That's not what you're going to get at first. After you use algebra to solve for dy dx, then you can use the given equation, right, which was e to the x plus e to the y equals e to the x plus y, to make some substitutions. So that then it will turn out to equal negative e to the y minus x. If you haven't already done so, I really think that you'd be well served to make sure you're spending time on the practice exercises. I know you're not turning them in to me, but if you're not doing them, you're going to feel stuck on every problem you try. The problem set intentionally has problems that are harder. And if you're, if you don't spend enough time on the practice, then you're just jumping into the hard things without giving yourself enough time to kind of build up your skills with the derivatives of these functions. Any other questions you want to ask about today?
I'm all set.
Okay.
Yeah, I'm good too.
Okay. If you want me to look at a draft of your problems before you turn them in next week, I'm happy to do that. Right, for today, your focus is probably on finishing up that quiz and submitting that by the end of the day. If you have any other questions on that, just let me know.
Thank you.
Thank you. Enjoy the rest of your day.
Thank you. You too.